Welcome back to Very Ordinary Differential Equations. In this lecture, we see how everything we've learned about Laplace transforms and their inverses can be used to solve differential equations. The crucial theorem that brings together Laplace transforms and differential equations is this one. Suppose you have a continuous function on the non-negative real numbers. If the absolute value of this function is less than some exponential function, okay, so our function is just smaller than some exponential. This is a very general requirement. This guarantees, for example, that the Laplace transform exists. Suppose also the derivative of f prime exists and is piecewise continuous. Then the Laplace transform of the derivative exists. This is background general theory, but the real important part for generating solutions is the next line. The Laplace transform of f prime is s times the Laplace transform of f minus little f of 0. We're actually going to prove this statement, unlike many other things, because it's so helpful and it's not that difficult of a proof. It also helps us to get more familiar with Laplace transforms to prove this statement. Since f prime is assumed to exist and is piecewise continuous, we're just going to attempt to go ahead and directly compute the Laplace transform of f prime, and we're going to see that we will get out this quantity here. The Laplace transform of f with s factored out minus a constant f of 0. So let's go ahead and prove that statement. So first, let's go ahead and just start with the definition of the Laplace transform of f prime. It's the improper integral, 0 to infinity, e to the minus st f prime of t dt, because we're computing the Laplace transform of f prime. We're going to apply integration by parts. So we already know how to integrate f prime. Integrating f prime would just be f. So applying integration by parts, making this u and this dv would give me u times v evaluated at the endpoints minus the integral of v du. Now the derivative of this would kick out a factor of minus s. So when I subtract that, I get a plus s times the integral of v du. Now this s has been factored out, and look what occurs here in this second term. This is just s times the Laplace transform of f. Also in that first term, we assumed that f of t in absolute value is less than or equal to some exponential, and s is going to be bigger than the exponent here. Therefore, I have e to the minus st times something smaller than e to the minus s naught t. When I combine those two things together, this exponent is more negative than this one because s was assumed to be bigger than s naught. Therefore, as this upper limit goes to infinity, we basically have a more negative exponential times something smaller than a less negative exponential. Overall, this looks like a negative power on an exponent, and as this goes to infinity, that will go to 0. And the second improper integral is just s times the Laplace transform of f. Therefore, what we have is this limit evaluates to 0. I then subtract, plugging in a 0 here. That would give me a 1 times f of 0. And my second term is just s times the Laplace transform of f, which is exactly the claim, that the Laplace transform of f prime is s times the Laplace transform of f minus the constant f of 0. There's a similar result we can establish for the Laplace transform of f double prime. So we're going to make all the same basic assumptions. You know, the function is smaller than some exponential, but we're also going to assume that f double prime is piecewise continuous. Well then, the Laplace transform of f double prime is s squared times the Laplace transform of f minus f prime of 0 minus s times f of 0. The proof is actually quite fast. So the first theorem said L of the derivative is s times L of the function minus the function at 0. But now my function is f prime. So what's the derivative of f prime? It's f double prime. So L of the derivative is s times L of the function minus the function at 0. So we've already proved this. And now we're just going to apply this theorem again to L of f prime. L of f prime is s times L of f minus f of 0. Once I distribute everything out, we get exactly the claim. S squared L of f minus s times f of 0 minus f prime of 0. You can do similar things to get Laplace transforms of f triple prime, the fourth derivative, etc. We don't need them right now because we're only applying ourselves to second order equations. So the highest derivative that's ever going to appear for now is the second derivative. So we're going to stop here in deriving more. Okay, but it is totally feasible to derive more and more equations for Laplace transforms of higher derivatives. We just don't need them. So what's our general technique? We have a formula for L of f prime, but we also have a formula for L of f double prime. So given a linear differential equation, whether it's homogeneous or not, we apply the Laplace transform to both sides. We solve for capital F of s, then find an inverse Laplace transform. So for now, we're only going to apply this to constant coefficient differential equations. We'll see why in a moment. But the basic idea is apply the Laplace transform to both sides, isolate capital F of s, then inverse Laplace transform to get your original solution f of t. So let's begin with an example. Use the Laplace transform to solve y double prime plus y prime minus y equals 0 with the initial conditions y of 0 equals 1, y prime of 0 equals 2. So first we take the Laplace transform of both sides, but remember, we know how to take the Laplace transform of a derivative and of a second derivative. We have formulas for that. So throwing the Laplace transform at both sides produces the Laplace transform of y double prime plus the Laplace transform of y minus the Laplace transform of y equals the Laplace transform of 0. We've simply taken the Laplace transform of everything here. Now on the right-hand side, the Laplace transform of 0 is 0. There are two basic ways you can show this. First, you can just use the definition and compute what is the Laplace transform of the constant 0 function. Alternately, since we know that the Laplace transform is a linear operator, when you plug in 0, you have to get out 0. So now what we do is we solve for L of y. Up here, we have s squared L of y, s L of y minus 1 L of y, and our constants that don't involve L of y are y prime of 0, sy of 0, minus y of 0. So collecting terms according to whether they do or do not have L of y involved will allow us to factor like this. S squared plus s minus 1 times L of y plus negative y prime of 0 minus the quantity s plus 1 times y of 0. Now we can solve for L of y by moving this entire term over to the other side and dividing by s squared plus s minus 1. So here is the Laplace transform of y. So we found that the Laplace transform of y must be y prime of 0 plus s plus 1 times y of 0 over s squared plus s minus 1. Of course, we had initial conditions. Y of 0 is 1 and y prime of 0 is 2. So we end up with a 1 here and a 2 there. Overall, we get 3 plus s in the numerator. So now, whatever y is, its Laplace transform is 3 plus s over s squared plus s minus 1. And we're trying to find the solution y, in other words, an inverse Laplace transform of this rational function here. So that's all we have to do, find an inverse Laplace transform. The denominator is already of the form s minus a squared minus omega squared, if a is equal to minus 1/2 and omega is root 5 over 2. This is a denominator, s minus a squared minus omega squared, that can be found in many tables of Laplace transforms. I would note, this denominator does have real roots, so you can do partial fraction decomposition. But this form of a denominator will show up in many tables of Laplace transforms, and noticing that the denominator already looks like something that appears in a table of Laplace transforms, s minus negative 1/2 squared minus omega squared is going to help us a lot. So from a table of Laplace transforms, we find that shifted versions of hyperbolic trig functions give us these denominators of s minus a squared minus omega squared. However, our numerator should either be exactly omega, which was root 5 over 2, or s minus a, in other words, s plus 1/2. So we need to rewrite our numerator to match that general form. So instead of 3 plus s, we know we want s plus 1/2 to appear. this would leave behind s plus 5 over 2, but that constant 5 over 2 should actually be expressed in terms of omega, which is root 5 over 2. So it's root 5 times root 5 over 2, or root 5 omega, plus s minus a. So here's what we have. We took the Laplace transform of both sides. We eventually recognized that after we solve for L of y, we get a denominator that looks like something we can find in the table of Laplace transforms, but we had to make the numerator look like root 5 omega plus s minus a. So I can split this up into two pieces, root 5 omega over s minus a squared minus omega squared, plus s minus a over s minus a squared minus omega squared. Now, from our table of Laplace transforms, getting out that as a Laplace transform would have corresponding inverse Laplace transforms of e to the at hyperbolic sine omega t and e to the at hyperbolic cosine omega t. So now we have found a function y whose Laplace transform is this. Therefore, we have found a y that solves our original differential equation. What I would point out is that the differential equation we began with, y double prime plus y prime minus y equals 0, is a second order linear homogeneous differential equation with constant coefficients. We have techniques to solve that. We would take the complementary polynomial r squared plus r minus 1 equals 0 and try to find roots. We would find two distinct real roots, meaning our fundamental set of solutions should be two different exponentials. And that doesn't look like what we have down here. This doesn't look like two distinct exponentials, but it is. Remember that hyperbolic sines and cosines are in fact sums or differences of exponentials. And once you distribute this e to the minus t over 2 against each of these hyperbolic trig functions, you would get two distinct exponential terms. So this really will give you the same set of solutions, even though we will have found a different fundamental set of solutions. As a second example, let's use Laplace transforms to find all solutions to y double prime plus y equals 0. Now this is a differential equation that we may recognize the solutions to already. They're sines and cosines. So we take the Laplace transform of both sides. On the left, we get the Laplace transform of y double prime plus the Laplace transform of y. And on the right, we have the Laplace transform of 0, which is just 0 again. Solving for L of y, we get L of y is y prime of 0 plus sy of 0 over s squared plus 1. We can then manipulate this to be y prime of 0 times 1 over s squared plus 1 plus y of 0 times s over s squared plus 1, because 1 over s squared plus 1 and s over s squared plus 1 match forms from a table of Laplace transforms. These are sines and cosines respectively. So taking an inverse Laplace transform, we end up with y is y prime of 0, some constant, times the sine of t, plus y of 0 times the cosine of t. So we've deduced that y, to be a solution of this differential equation, must be y prime of 0 times the sine of t plus y of 0 times the cosine of t. For an arbitrary choice, in other words, a choice of initial conditions of y of 0 and y prime of 0, we therefore get a solution. Now, if we simply denote y of 0 to be c1 and y prime of 0 to be c2, we can move this around a little bit and get the more familiar looking y is c1 cosine t plus c2 sine of t, which is what we would have gotten for a general solution if we used our earlier techniques of solving second order linear homogeneous differential equations with constant coefficients. And finally, a third example. Use the Laplace transform to find a solution to y double prime minus 6y prime plus 9y equals negative 8e to the t cosine of 2t minus 9t plus 33. With initial conditions, y of 0 equals 5, y prime of 0 equals 10. Before applying the Laplace transform to both sides, we're going to want to expand the entire right-hand side to get terms that are easy to match to a table. Applying the Laplace operator to the left, we get L of y double prime minus 6L of y prime plus 9L of y. With our initial conditions that y of 0 is 5 and y prime of 0 equals 10, we can simplify this a little bit to just get s squared L of y minus 10, since y prime of 0 is 10, minus 5s minus 6s L of y this y of 0 being 5, this would distribute out to be a plus 30, 9L of y. Solving for L of y is our ultimate objective, so let's go ahead and collect all the terms that have L of y and factor it out. S squared minus 6s plus 9, and then all the terms that don't have L of y, 5s and 30, and a minus 10 here, giving me a minus 5s plus 20. I just noticed that I can factor a 5 out of that, and that might be handy later on. So here is the Laplace transform of the left. S squared minus 6s plus 9 times L of y, minus 5 times s minus 4. Now we're going to go ahead and apply the Laplace operator to the right-hand side, consulting a table of Laplace transforms as we go. First, the Laplace transform of negative 8 e to the t cosine of 2t, the constant negative 8 factors out. In any table of Laplace transforms will tell you e to the at cosine omega t has Laplace transform s minus a over s minus a squared plus omega squared. So here's the Laplace transform of this first term, negative 8 e to the t cosine of 2t. Next, we have to take negative 9 times the Laplace transform of t. The Laplace transform of t is 1 over s squared, so we just get negative 9 over s squared, and the Laplace transform of a constant is 1 over s. So the Laplace transform of 33 is just going to be 33 over s. Altogether, the Laplace transform of the right-hand side can now be put together as, well, this first term, I'm going to go ahead and distribute the negative 8 to give me 8 minus 8s over this denominator. Expanding all of this out would be s minus 1 squared plus 2 squared becomes s squared minus 2s plus 5. Here we have minus 9 over s squared. Here we have 33 over s. Now we are going to want to find a common denominator, but trust me, you want to not distribute that common denominator. Leave it factored. So we've applied the Laplace transform to the left and the right. On the left, we already had this here. And on the right, if we go ahead and find that common denominator and combine everything, you'll end up with this. Okay. So now the goal is to solve for L of y. So what we have to do is take this minus 5 times s minus 4, throw it over to the other side, and give it that common denominator, which is going to give us all of this times L of y is everything we had plus 5s minus 4, and now I've given it that common denominator. Now we're going to simplify this expression. So what we now have is that s squared minus 6s plus 9 times the Laplace transform of y is this enormous mess over s squared times s squared minus 2s plus 5. Okay, so that's what we would have gotten if we actually worked through all the algebra of combining the two terms from the previous slide. Of course, the goal is to get the Laplace transform of y by itself. So we're going to divide by s squared minus 6s plus 9, which is just s minus 3 squared, as many of you have probably already pointed out. And therefore, we end up with the Laplace transform of y is this enormous numerator over s squared minus 2s plus 5, s minus 3 squared. Now what we have to do is find an inverse Laplace transform. And as we've pointed out, if you want to find an inverse Laplace transform of a rational function, you do partial fraction decomposition. So what we have to do is partial fraction decomposition of this enormous rational function on the right. So here is what we have for the Laplace transform of y, and we have to perform partial fraction decomposition. So our factors are s and s squared. Here's my s squared. This was an irreducible quadratic, so it is what it is with a numerator of a linear term. Then for s minus 3 squared, we get a constant over s minus 3 and a constant over s minus 3 squared. And now we do the partial fraction decomposition, which through the magic of cutting and eliminating time, we find a is 3, b is minus 1, c is 0, d is 2, e is 2, f is 3. That will solve this huge mess. And therefore, the Laplace transform of y is 3 over s minus 1 over s squared plus 2 over the irreducible quadratic plus 2 over s minus 3 plus 3 over s minus 3 squared. So we're finally in a position that we can just hit it with an inverse Laplace transform. If this is the Laplace transform of y, well then, what has Laplace transform 3 over s? The constant 3. What has Laplace transform 1 over s squared? T. What has Laplace transform 2 over s minus 1 squared plus 2 squared. This is omega over s minus a squared plus omega squared. So we get e to the at sine of omega t. What has Laplace transformed 2 over s minus 3? 2 times e to the 3t. The 2 factors out, and this looks like a 1 over s minus a. That's the Laplace transform of e to the at. And here in any Laplace transform chart, you would find that the Laplace transform of t times e to the at is just going to be 1 over s minus a squared. And then that 3 in the numerator factors out. So inverse Laplace transforms of each of these pieces give me all of these. And here is my function y that solves the original differential equation. All right, all together, what have we got? The Laplace transform, or Laplace operator, provides a very powerful new tool for finding solutions to differential equations. The examples we've seen so far were restricted to constant coefficient second-order equations. We already have methods to solve those. However, we're going to expand our methods to account for forcing functions that are not elementary functions. So that last example was notable compared to the earlier ones because the forcing function was this big mess of various terms. Technically, we could have done that using, for example, the method of undetermined coefficients. However, what we're going to start doing is having forcing functions that are not elementary functions like sines, cosines, rational functions, etc. Instead, we're going to have forcing functions that are things like step functions or even what are called impulses that we can't just treat with undetermined coefficients or variations of parameters. The Laplace operator can also act on higher derivatives, okay, with much simpler results than other techniques that correspond to things we've done. So for second order equations, constant coefficients are quite nice, and the Laplace transform may seem like unnecessary work. But once you move beyond second, third order equations, the Laplace transform is a much simpler way to solve things compared to other techniques for constant coefficient equations. So at the second order level, it doesn't seem that useful, but trust me, the Laplace transform is a wonderfully powerful, useful way to solve differential equations. Since we're not really doing such examples right now, you have to take my word for it, but do keep it in mind.